Okay, great. So let's. I think we were looking at the proof for simulation, backward simulation. So the context here is that we are trying to prove that assuming the properties about the simulation relation, we can prove that there is trace inclusion both in the forward direction as well as the backward direction, right? So just to recall um, our understanding. So here is what we mean by forward and backward, right? If this generates some trace, then this also generates some trace, right? S2 also generates the same trace. That's the forward one, and the backward one is if S2 generates a trace, and S1 also generates the same trace, right? Forward is a little bit easier. Backward, we needed to use this notion of totality and determinism. We have used totality. We haven't used determinism yet. So we will sort of look at that today, right? So we are halfway through the proof. We discharged one of the sub goals. Essentially, we are inducting on the generation definition of traces, right? We were doing induction on this definition. There are 4 cases for generate. One was um, the empty trace, right? So you can always truncate the trace. That is easy. The other one is skip. So that is what we did. So for skip, we had to show that the trace would be a none, right? So we had shown that as well. We need to show the other 2 cases, which is a silent step, right? And the step that actually emits an output. So let's do the silent step now. So as we did earlier, we are going to look at what we have in the context, and then we are going to slowly expand this, right? So what do we have here? So we see that R is related to VC1 is related by R to VC. VC1 is related to R by VC. And then we have a silent step from VC to VC prime, right? What is a silent step? It's some small step where we don't output anything, right? So we know that these are pair of values. Let's do cases to just bring out that fact. So when you do this, all that does is breaks that VC into subcomponents. So what do we have now? It's the same thing, right? So VC, V comma C is related to V0 C0. V comma C is related to V0 C0 by R. And then from V0 C0, you can take a silent step to VC prime, right? So we need to show that, what do we need to show? We need to show that the other side will also take a step and that label will also be the same, right? That is what we need to show because we are asked to show that V comma C generates NS, right? V comma C generates NS, assuming that, where is the other one? VC prime generates NS. So if VC prime program sort of from that state generates a trace NS, then V comma C generates an NS. The one way to show that is to say, okay, this also generates takes a step, right, which is a single step with silent label, right, and that will be at that point. What you will have is that you will have both the induction hypothesis, and this part of the diagram will be the same as what we have currently. So we can prove it by induction. In order to do that, we need to show first that V comma C can take a step, right, or is already a skip. So we will use our skip or step, the totality property first, right? We will just do that and start looking at this. So as earlier, we simply bring this assertion, which we already proved, into the context, right? So we sort of bring it into the set of assumptions. So all this does is it brings an additional assumption, which says that you can take a step from here, or this is already a skip, right? So let's break it down. Okay, so now there are 2 cases, right? First is the command is C command is already a skip, right? Or you can take a step. So firstly, let's look at that, right? So if V comma skip is related to V0 C0, by definition of agree on termination, we know that C0 must also be a skip. So let's do that first, right? But if you because of the property and the fact that we have an assumption that we can in fact take a step, we can derive a contradiction. So observe what we have here, right? It says that, oh, you can actually take a step from skip to VC prime. This is not possible. So we will just invert that, keep inverting that to derive a contradiction just like before. So if you derive this, you will get to a point where there's a step 0 from skip. That is not possible. So once you invert it, that proof goes through. The next step is actually you can take a step, right? So this is what we have at that point. So from VC, I can emit a label x0 and then go to xx1 and then go to x1, right? And now, if you sort of look at it, what we need to do is we need to show that x0 is in fact none, right? We need to first do that so that this will match one-to-one. So in order to do that, what we first do is to specialize this one-step function. What does this one-step function tell us, right? One-step function relates these two states exactly with the label, right? If v comma c takes a step in by emitting a label x0, then v0 c0 also takes a step by emitting the label none. The same label. Because it is the same, it must be the case that x0 must be equal to none, right? That is the argument that we are going to use. We are going to take advantage of the assumption that our simulation relation helps us match the steps one-to-one, right? We are just going to plug in the relation here and the c-step function here, right? So there is an expectation of relation and c-step, right? So I'm just going to do plug one step by h1 and h2. H1 is this relation, right? All it does is it plugs in the universally quantified variables with actual things, right? For VC1, VC2, it plugs in with v comma c and v0, c0. And h2 is the step function. And for that, I'm going to give, this is the step function. And for that, I'm going to give h2 as the argument, right? And I don't know whether we've seen this static. Specialization simply says if you have a hypothesis which has, say, P arrow Q, you can specialize it by applying a particular argument, which, say, for P, which will specialize just Q, right? So that's the idea there. So that is what we are doing here. So we are just applying it here. So once you do that, you will see that the one-step function is now going to be specialized, right? One step is now only having the exists. And where does this exist come from? This is just the part that lives here, right? But all of the variables will be specialized as well. So all of those are specialized to whatever we have, right? Okay, and then we have an existential with the conjunction. We are just going to use first order again to break it apart. Okay, so here is the interesting bit, right? So far we've used only totality. What this tells us, one step tells us is that if VC can step to something by emitting x0, one step tells us that v0 c0 can also step by emitting x0. But we also know that our semantics is deterministic, right? If v0 c0 can take a step, then the target state and the label should be the same across any kind of different steps, right? There is only one deterministic step that you can take, which is what we will use here. This is the thing that we had earlier, right? That C step V0, C0, none VC prime. That's the one that we had. Additionally, thanks to one step, we now, sorry, not this one. We now have this C step as well. So what is this? It says that from V0, C0, I can emit the label X0. X0 comes from this side, right? And go to X2. And what do we know about our operational semantics? It is deterministic, which means that these two, right, should be the same, which is x0 should be none and x2 should be VC prime, right? Which is what we proved earlier using determinism lemma. We are just going to apply that determinism lemma on H. You can look at the details of what it does and the simplification and so on. But if you apply an E auto, we will learn that x0 equal to none, right? This x0 equal to none, and x2 equals vc prime. That's the variable that was introduced there, and that is equal to vc prime. So now you can do propositional to break this apart, and subtractic substitutes for each of these variables. So let's do that. Okay, so now what we have? We need to show that VC generates NS, right? V comma C generates NS, and we have VC prime generating NS. But now we actually know that VC XX1, right? VC to XX1 also emits a silent label, thanks to our reasoning this way, right? Because these two are unified, we know this is going to be none as well. And we are going to use this induction hypothesis. We will come back to that. So firstly, what we are going to do is that we are going to take this obligation, right, which says that I am going to generate the trace ns from VC into saying I am going to generate the trace ns from XX1 because I know that from VC I can take a silent step, right? So I'm going to use this reasoning. So the way I use that reasoning is that I'm going to start from the state, I'm going to take a silent step. I will be asked to show that I can take a silent step, which is the hypothesis that we have, right? So I am applying gen silent. Because of this application, it asks me to show that you can take a silent step from VC, right? Which is what I have here. So E assumption makes it go through. And then the proof obligation that I have, the goal that I have is generate XX1 NS. And at this point, I can apply my induction hypothesis, right? Which is here. So this is for all VC1 NS. So I'm going to apply that. And if you do it, then all we are expected to show is that this VC1, which is specialized to XX1, is in fact related to VC prime, right? This was thanks to this one-step function, which in addition to showing that we will emit the same label, it also showed that the target states are also related by the same relation, bisimulation relation, right? That came from that, and we can make this proof go through as well, right? So that is discharging the proof for emitting a silent step. This is the proof for emitting. So the next sub goal is emitting the proof for this next sub goal is showing that I mean handling the case where we actually output something. It's not a silent step anymore, but the proof structure is essentially going to be the same, right? Just the same argument. So first we are going to break VC1 and VC to their show their constituents, right? And VC is related to V0 C0, VC is related to V0 C0, and there is a C step from V0 C0 emitting an output, right, to VC prime. Again, we are going to do the same idea. So we are going to show that this can either be skip or take a step. We will show by contradiction that this cannot be a skip. If it is a skip, then this has to be a skip. And if it is a skip, then we can't take a step, right? So that's, we first bring that into context. We break it apart and then, yeah, so here we have a contradiction, right? So it says I can skip from skip. This is not true. So inversion makes it go through. And again, we are at a similar position, right? Instead of none here, we have some n. So we specialize again. We do first order. And we will apply determinism, right? If you look at H3, it says V0 C0 can step to X2 by X0. But we know earlier that V0 C0 can step to VC prime with some n. So by determinism, these two must be the same. So let's do that. So you will see this. If you do substitution, that makes it go through. And actually, I've expanded. So I've actually stepped through here with E apply, E assumption, IH generate, and so on. but eauto actually makes it go through because we've added all of those constructors as hints for our auto tactic. So eauto actually makes it go through. What it's going to do is it's going to apply gen output first, and I will be asked to show that I can step from VC by emitting some n to XX1. That will go through here. Then I will have something which I can apply this I had generate this induction hypothesis to show this relation, which is what I will have here. Yeah, so if you want, you can do info eauto, right? So, and that will show the steps. So yeah, so we've done backward now, right? So backward was a bit interesting, but we've done backward as well. So just like earlier, we are going to show that trace inclusion holds, right? And this is simply just unfolding the definition and applying this by eauto. There is nothing interesting here, just like what we had seen earlier. So now that we have both um, the inclusions, right? So from left to right and right to left, we can actually show that they are the same traces, right? And again, this is just a unfold of trace equivalence, which asks to show both of these individual ones. Actually, all of these are not necessary, right? This is just in the context, but we are not going to use them anyway. So we split it, and then you just show each one separately. That's done. So what we've shown at the end of the day is let's go 2 slides right to this. Okay, what we've shown is using the simulation relation and these assumptions, we've actually shown that the traces that are produced are the same, right, for these two commands. If you take two states which are related by this bisimulation relation, then they will emit the same traces, right? We are relating two program states by trace equivalence. Let's now use them in order to show that constant folding as we've defined, right? So we can fold maximal sub-expressions which only have natural numbers, right? And then operations over natural numbers. Let's actually show that that particular optimization preserves the traces. So the first thing that you have to do for this is actually lift that to step 0, right? So this is actually this particular step is not I mean very interesting. All it says is we have V1 C1, and if we can step to V2 C2 by by emitting a label L, right? Then we are saying that from the optimized program C-fold expression on C1, right? You can emit the same label and go to C-fold expression of C2. So this is simpler proof if you think about it, because we are not proving the equivalence of two states, right? All we are saying that if you have unoptimized program which can take a step, then the optimized program will also take a same step, right? So this is just a single step. We are not actually relating the traces fully, right? We are just talking about a single step, right? And observe that why is this not complicated? Because we are talking about a single step, and we are only using inversion. We are not inducting on. We are not using induction. So we are not reasoning about all the traces. We are just reasoning about just a single step, right? Yeah. So the automated thing is here, but yeah, you can read through this automation and figure out what it does. But this is uninteresting, right? This will just go through. If you start with invert 1 and simplify, the proof will just simply go through. I'm not going to go into detail here, but observe that what we are saying is that if you start from C1 and can go to C2 by emitting L, you can go from the optimized program by emitting the same label and go to the optimized version of C2, right? So that's done. Then there are a little bit of additional lemmas, right, to describe the constant folding over contexts, right? So here is here is a function, right, which takes a context, an evaluation context, and returns you another evaluation context, and it tells me how to apply constant folding on this evaluation context. Evaluation context is just like a command, right? And all it, the difference is that it sort of lacks, I mean, it has all the richness, but it lacks this particular, it has a single hole, right? And that is what we're doing. So if you, the important bit is if you have a context, right, we recursively apply the same function. But for the command part here, we are actually applying C-fold expressions. And C-fold expressions is our definition of constant folding, right? So this, basically this function tells me how to apply constant folding on evaluation context, right? So that's the takeaway here. What else do I have? I have how to constant fold over the plug relation, right? This is a bit interesting. I mean, the proof is again very simple. It says that what does plug say, right? Plug is a relation that captures the relation between an evaluation context, a command that is used to plug the hole, and what is the command that you get as a result, right? If you plug C with C1, then you get C2, right? That's the thing that you have. What we have here is we are saying if this property holds, which is C of C1 equals C2, then if you fold constant fold over the evaluation context C, which is referring to this particular function, and you plug that hole that is still there in that constant folded evaluation context with the constant folded expression C1, right? Then you get constant folded expression C2. So this is sort of talking about how to fold over the plug relation. The proof is simple. Again, this will just go through. I'm not going to go through in detail, but reading it in the back of the mind is useful. So let's also add it to the automated resolution so that eAuto can make this go through. Okay, so that's all done. Now we are actually going to prove our main correctness property, right? Which is that what are we saying here? So in our language, take the state where you have B comma C, and the traces that are produced are equivalent to the traces that are produced by the optimized program, right? So this is trace equivalence, just to recall, and all we are claiming here is that the traces that are produced by V comma C is the same set of traces that are produced by V comma C fold expressions. We've done all of the hard work, right? We just have to, in order to show this, sorry, one. So in order to do this, what all we have to do is to plug in that relation, right? We have to produce a bisimulation relation, right? We have to sort of give a bisimulation relation that has the two properties. So we need to provide a bisimulation relation that tells us how to relate two states, right? And then we also have to prove that one step and agree on termination holds for that relation, because one step uses R as well as the agree on termination uses R, right? We proved that bisimulation relation preserves traces, assuming that one step and agree on termination holds, right? What we are going to do is to provide this relation, prove that one step and agree on termination hold, and because of that, we get the proof for the trace equivalence, right? So that's what we are going to do. And the way we do that is, yeah, so this is very much similar to how we did invariant weakening, right? So we said here is how you invariant weaken, and then we sort of prove with invariance. So this is very similar, right? So we first simplify, and the relation that we choose is exactly the same as what we want to prove. This is unsurprising. We want to relate the two states, right? VC1 and VC2, right? And for that, I'm giving an assignment for R here. For that, the way I'm relating that is, I'm not going to change the valuations. The valuations are going to be the same, right? First of VC1 is going to be the first of VC2, and the second of VC1 is going to be equal to the constant folded, second of VC2 is equal to the constant folded variant of the second of VC1, right? So this is the same as what we have stated here, but it's just unsurprising. This just is what we want, right? So when you do this, we end up with a bunch of subgoals. So this is one step, right? This whole thing is one step, right? Which is agree on termination. This is agree on termination, right? And this one is just asking us to show that this relation just holds on the state, right? What we wanted to prove. This will be obvious, right? So these two are simple. This is agree on termination. This is one step. And this is the simple relational thing which we just need to show. Because we picked exactly the one that looks like what we have here. It simply goes through. Yeah, the three subgoals correspond to two hypotheses and the one variable that we introduced. So I think I introduced this notation much earlier, which is just to, when I have three subgoals, I'm just focusing on the second one first, right? So the second one is agree on termination, right? So if this is skip, let this also be a skip, right? And if you simplify, we just get the version here. This is easy because why is this easy? Because if this is skip, we need to show that constant folding over skip is also a skip. We know that is true. There are no expressions here that has to be true. So that goes through, right? And let's focus on this one again. So here we just need to show that the relation actually holds on whatever we want here, right? So first of B comma C is first of V comma C fold expression C, which is first of this whole thing, right? And second of VC2, second of this term, right, is equal to C fold expression of second of V comma C, second of VC1 is V comma C. That's the initial state. And this again is very simple. This, if you simplify, you will see. Because we picked exactly what matches the structure here, it simply goes through as well. So that is also done, right? Now let's simplify this for one step. For one step, right? So here, what we are going to do is we are going to actually show something by proving something on. So what do we need to show, right? We need to show that if under this relation, right, if the left-hand side takes a step and emits a label, the right-hand side also emits takes a step and emits that label. So let's find out. So VC1 is the left-hand side, right? And I want to show that VC2 also takes the same step, right? And the property, the relation still holds, right? Relation still holds between the resultant states on both the sides, right? So just to show you, so this is one step. So if the left-hand side takes a step, the right-hand side also takes a step, and this relation still holds. And the only difference between the relation R here is just going to capture the notion of constant folding, right? So that is the assumption that we have here, right? This is the relation that we introduced here. I need to show that the relation holds on the final states as well, right? So in order to do that, I'm going to learn something from this H0, which is this step function, right? Here is where we need to sort of here is where all of the helper lemmas come in. Actually, I don't think it's instructive to go through this in detail. At this point, I expect you to look at the definition and follow it. There is nothing interesting going on. We've proved all of the interesting cases. So this is just a matter of applying the right lemmas here. So what we first do here is we actually show that if you can take a step, then you can take a similar step where you constant fold on these two expressions, right? This is what we proved with the step 01. I'm going to do that. So you get constant fold expressions here. The reason why we get to this is we are going to show constant folded expression on C2 here, right? So that will become clear when I do this. So yeah, then break apart VC2, simplify and substitution, right? So I need to show a C step. This is essentially, you can just break it apart, right? What is C step? You apply this constructor, this will give you a plug and so on. All of that you can step through. If you just do this step by step, you will see that this all matches one to one. Yeah, and then the rest of the proof is very trivial. Actually, let me not go through in detail. I think me talking about this is not going to be very helpful. But this is very, very simple, right? We proved all of it. The only interesting bit is this, right? So from here, where we had a step 0 on the left-hand side, right? We sort of use this idea that if we can take a step 0 from C0 to C prime, then we can also take a step from constant fold at C0 to constant fold at C prime. That is what ties in both of the unoptimized and optimized programs. And once you do that, the rest of the proof is very, very simple. You will see that this is a pattern that comes often, right? Because we picked this relation, we have to sort of relate that information somehow down the arrow as well, right? So this is the relation that is connecting this. I have a relation again here. I mean, this is R, inverse of R on this side, but R this side. I have to sort of get this information through down this arrow, right? This is a step, and that is what this particular step is helping us do. Step 0, we are sort of getting this C-fold expression, which is the relation that we captured here, right? Down this, and we are relating it again. You will see this pattern over and over again. I mean, we will see one more example of this. You will see the same pattern there. Yeah, so that's the proof. So typically what happens is, so all of this, what we've seen here, right? This is all sort of boilerplate. I've gone through the detail of the proof here. So this actual simulation relation is just boilerplate for us now, right? Because we don't have to do this every time we want to prove, say, a compiler optimization. Because under this assumption that we have this simulation relation R, we can prove, if you can produce a simulation relation that has these two properties, then you can go ahead and prove your optimization, just like what we've done here, right, with this constant folding. And all you have to do, your obligation is that you will have to show that the relation, the bisimulation relation that you pick is actually a bisimulation relation by which the relation has agree on termination property and the one-step property. Right, so this is what we've done. Observe that if you want to use this idea again, this is really what you need to do, right? None of the earlier things are necessary because they are part of the meta theory. We proved it once, we are going to use that idea over and over again. So in your assignment, you will have to use this particular simulation relation. All of the boilerplate will be given to you. You have to come up with an interesting way of proving certain optimization, right? So we will prove simple code motion, which is that you can move assignments around in your program. This is what we do, right? If you sort of think about what we do with loop invariant code motion, right? So you have a loop in which you always write x equals 0, or you write x equals y, where y is not a value that is changed by the loop, right? Then you can move that assignment out of the loop. because you don't have to do that assignment every time. So this is loop invariant code motion, but there is a simple code motion. The notion of this can be true even with two statements, right? You have some complex command, you have an assignment here. When can I move this assignment over here? Whatever is being assigned in this command could be a complex command, is not being used by the expression on the right hand side of this assignment. So if it is the case, you can move this assignment above, right? If they are completely independent. So this is an optimization that you will have to prove in your assignment. You will use this one-step evaluation. Again, it will use a slightly different definition of how we go about proving this, but the core idea is going to be the same. Okay. So any questions on this before we move on to a slightly more interesting way of doing optimization? So this is the style of optimization, the assignment that you will see, which is again going to do something very similar, is the style of optimizations that are used by ComCert compiler. So whenever you need to prove certain two steps are correct, you will have to go through a very similar one. So you'll do that in the assignment. I think you can read the assignment and find out what it is. No questions. Okay, so if there are no questions, let's move on to the next part of the same lecture. So the downside of this particular optimization, right, this particular simulation relation, is that the one-step function is exactly matching one-to-one, right? It's saying if you take a step on the left-hand side, then you have to take a step on the right-hand side. But oftentimes what optimization does is it removes certain constructs, right? If you say you have a loop and the entry to the loop is if 0, or actually in our case, what we will do is we have this if statement, right? And the predicate is going to, if the predicate is known to be always true, right? You can eliminate the false case, you can eliminate the if, right? And then you can take the body of the true case and then inline it at that position. But observe that that particular optimization cannot be proved with the infrastructure that we've developed here. Why? Because in the original program, you would have taken a step for if, right? If the expression evaluates to a value, then you go to this body, right? But in the optimized version, the if is gone. So you have to somehow reconcile the fact that the unoptimized program might take several steps. The optimized program can take that in a single step, right? This is one style of what optimizing compilers do. So, but you can also have the other way around, right? That a one step here can introduce multiple steps in the lower phases of the compiler. This is very true when you sort of compile programs down to assembly, right? A single write might be converted to multiple writes. Yeah, so you have an expression which is E1 plus E2, say times E3, right? And this is a single statement in your source program. But if you sort of look at how assembly languages look, they do addition, multiplication, each one in a separate instruction, right? So a single abstract instruction in the source language might translate to multiple instructions in the target language. Now, in order to prove the correctness here, you have to sort of do something different, right? You have to say, okay, I have a single step here. What are the different number of steps that can map down to this one single step in the source program? So this is also covered in the book, but I'm not going to cover it for our course. What I'm going to cover is the optimization technique, right? Multiple steps here in the source program translate to a single step. And how do we actually define the simulation relation and apply the simulation relation to prove certain optimization. In particular, we are going to optimize away if statements where you know that the predicate is always going to be at compile time some constant value. Okay, so that's what we are going to do. Let's switch to the slides to study that. So yes, okay. So here is I think this should be not equal to. Yeah, so that should be not equal to. I said equal to, but so the relation that the optimization that we are going to define is this one, right? I have this is an if, right? If E1 then E2. If you know that E1 is always true, E1 is not equal to 0, then this whole thing can be just E2, right? And that's the optimization that we are going to describe now. We can no longer use our basic simulation because we intentionally skip steps, right? So our optimized program does not have the when, so we cannot match it one-to-one. So we have to do something interesting, right? So before we actually look at the correct version of the simulation relation, we can start with the faulty version, right? The correct version has some complexity. In order to motivate that complexity, we will look at the faulty version. This is similar to what we have seen earlier, except we are going to say something about this multiple step on one side, right? We are again going to define a simulation relation with skipping, right? That is again a binary relation, right? And again, we have this agree on termination property. If the left-hand side is already skipped, the right-hand side is also skipped, right? But this step function is going to be a little bit interesting. It says that if S1 is related to S2 and S1 steps to S1 prime, emitting a label L, then two things can happen, right? Because you can take multiple steps here, we are saying that you can take a silent step. So you can take a silent step where say in this case a silent step will be execution of this when case, right? Step if that's the silent step. You can take a silent step, but what we expect when you take a silent step is that the silent. My phone is ringing, so what do you do when you take a silent step, right? So when you take a silent step, you want the target of the silent step to relate to S2, right? This is when you actually eliminate a particular construct. So I've eliminated when. So when is gone. So I will say that you can take the step. This is not going to do any output. That's the main thing that we want, right? We are going to match on outputs. So you can take the silent step, but if you do take a silent step, then it better be the case that the target is related to the original S2, right? That is one. And the other case is the usual one, right? So all of the usual ones where you don't eliminate. So if you take a step from S1 to S1 prime by emitting a label L, then there exists an S2 prime, right? Such that S2 can step to S2 prime by emitting the same label L, right? And S1 prime and S2 prime are related by the same relation. So this is the elimination, right? Intentionally skipping things, and this is what we had earlier. So what this allows you to do is to skip multiple things, right? Keep doing skipping until you actually take a useful step at some point, right? So this looks okay on paper, but I wouldn't call it faulty if it didn't have a fault. So let's see where it breaks down. So here is a faulty optimization. Okay, so this optimization is invalid. What it's going to do is to add advertisements in a very specific function. By advertisement is just going to keep printing some stuff, right? So here is a program. Consider this program, right? It's a while loop. It's an infinite while loop that never terminates and just skips. So this program never terminates, but it also never outputs anything, right? So everything is a silent transition. I'm going to optimize this with this broken with ads optimization, right? Optimization did not optimize. It's just some function that transforms the program, right? And the transformation that I do here is that I'm going to infinitely output 0. Um, there are two problems here. Firstly, this is not an optimization. Secondly, Even if you think this is an optimization, it is breaking our definition of what an optimization shouldn't do, right? It is actually changing the output behavior, right? If you have a skip, it is actually changing that to out 0. So this is producing more outputs, different outputs than different traces than what the original program outputs. For all other C's, I'm just going to leave the C as such, right? This is like a very specific broken optimization. The problem is that this particular optimization can be proved correct with this way of formulating by simulation. So we can use the following candidate simulation relation, right? What is a simulation relation? We are just going to relate the states, right? And this relation could be anything. So it just needs to somehow relates parts of it so that it is reasonable and not relate other parts of it. This relation is going to look very strange, right? This relation is supposed to be a binary relation, right? So it's somehow saying relate. I'm going to relate P1 C1 to V2 C2, but observe that I'm not even mentioning C2 here, right? All I am saying here is this relation holds when C1 is exactly while one do skip or skip semicolon while one do skip, right? This is very strange. The reason I picked that is that I'm going to show that this particular program can be proven correct according to our definition, right? This is very, very strange relation. For everything else, right? For every other command in C1, this is not going to hold. It only holds for while one do skip and skip semicolon while one do skip. So you can sort of see why I've chosen this form. This is exactly what I have here, right? And this is what you do when you do one step of while, right? The body of the skip, the body of the while comes over here. So you get skip, semicolon, the whole while loop again, right? And how can I prove this? Here is the way, right? Because I can, the expectation here is that I either take a silent step or take a step that matches. I can always take a silent step here, right? This is read to be this is supposed to be 1. It looks like an L. That's the problem with the font. So from while one do skip, I can take a silent step, which is going to be skip semicolon while one do skip, and this is related to the original relation. Again, this is also related because all I say here is I don't even mention C2. All I'm saying here is that C1 is either this form or this form, right? And this is always related to any command at all. It is also related to this command, right? And from here you take a step, silent step, go back to while one, right? So this is a relation that holds actually, and because this relation holds, I should be able to prove with that faulty version that this optimization preserves the output traces, right? Trace equivalence holds. But obviously, trace equivalence does not hold because we know that when we execute this program, you get no traces. When we execute this program, we get traces which are like infinite outputs of 0. So that particular definition is broken, right? So we have to fix that definition. And the intuition, the idea is very simple, right? Because our program is sort of going to execute a number of steps, right? You cannot infinitely remove steps from the optimization, right? So if you take infinite number of steps, you cannot remove all those infinite number of steps. You can only take a finite number of steps in this fashion. So in particular, what we are going to restrict is that you can only do finite number of these steps before you actually have to take a real step where the label matches the label on the other side. You cannot keep doing this whole thing over and over and over again, right? So that's the problem here, right? So that's the problem here. We are actually going to eliminate that. We are going to put a fixed bound on the number of times that you can do this. And if you put a fixed number of times you can do this, eventually this is going to break down, right? You can't show anymore. You can't keep doing this. You have to pick a number where it terminates, right? So That's the idea here, right? So this looks similar to the earlier one, but this is the right version of simulation with skipping. The idea here is we index the relation by n. There is some n which we use as an index. We say that an n index family of binary relations, right? So R1, R2, R3, and so on. There is just an index which is interestingly used somewhere, right? For this relation Rn, again we agree on termination, right? If it is a skip, then C2 also has to be a skip. This is the interesting one, right? If S1 Rn is related to S2, S1 Rn is S1 is related to S2 using Rn, right? S1 is related to S2 using Rn, and S1 takes a step, which is a label L to S1 prime. S1 takes a step, S1 takes a step. If it can be of two kinds, right? The first kind is this one, right? So if n is greater than 0, then you can take one of these steps, right? Where L is a silent label. And then what you do is this S prime should be related to S2 in Rn minus 1, right? So that's the limiting factor here. So you start with Rn. If you choose to go down this route, you reduce the number of ways you can, number of times you can step through this, right? So you can only do the silent transitions n number of times, where n could be arbitrary natural number, but it cannot be infinite. We know that natural numbers, as you keep subtracting, should become 0, right? So it reduces each step. Eventually, it has to reduce down to this step, right? The step here. It says that you can step from S1 to S prime, emitting some L. You go similarly, you can step from S2 to S2 prime by emitting the same L, right? And what happens to this N? So the thing that happens here is this particular N is only specific to this relation. Once you actually take an interesting step, right? There is no relevance to this n. This could be arbitrary other n prime, right? This n prime could be any arbitrary number. It's a natural number again. So you can again apply many steps of this one and then do many steps of this one, right? So this n and n prime are not related. The important bit is the relation between this Rn and Rn minus 1. So you can only do finite number of steps of the second case. And that prevents us from proving that this program, this optimization is actually correct with respect to simulation, right? So this is what we are going to do in the second part of the compiler optimization. And the example that we are going to adopt is elimination of ifs, right? So when you know that it is not equal to 0, this has to be not equal to, then we can do this optimization. We are going to prove this optimization, right? So we will do that in the rest of the week. I'll stop here for now. Any questions on this definition? Right. So it looks a bit hefty, but it's all of the details are there for a reason. Right? So, but if you sort of imagine in terms of the pictures, it's much simpler. Any questions, comments? Okay, if there are no questions, let's stop now. Then we can continue tomorrow. Thank you. Bye bye.